Yes, class. Is it audible now?
Yes, ma'am.
Okay.
Yes, ma'am.
So yesterday, not yesterday, on Tuesday we stopped it here, and we had completed the charge densities. Now the last topic, were we discussing these charge densities? Because we have to see the application of Gauss's theorem. So firstly, for any question of Gauss theorem, we draw a Gaussian surface. Now, what is this Gaussian surface? The Gaussian surface is basically a geometrical shape that we draw to enclose the surface. See, what we have studied, we have studied that Gauss law is applicable only for closed surfaces. So we require closed surfaces, we need closed surfaces, right? So for that purpose, if the surface is not closed, suppose if you have an open sheet or if you have a straight wire, then what we have to do in such cases, we will draw the closed surface by ourselves, right? That is what is Gaussian surface. Like suppose this is a wire, this is having some charge. So what we can do, if we draw and enclose this in a cylinder, in this cylindrical figure, this becomes our Gaussian surface, all right? And we can follow the linear charge distribution. If we have sphere, then for sphere, the only solution is to draw another sphere. So spherical Gaussian surface can be. So there are three figures which we have to use: a straight wire, a thin sheet, and sphere. These three applications are there. Let us just complete it today so that we end this chapter. Write down this part, then I'll start with infinitely long part. Just write this page first. Done, class?
No, ma'am. 1 second.
1 minute.
Okay, okay. Take it. Okay. Now see, we have a straight long wire with us. We have to calculate the electric field due to infinitely long wire. Now see, infinitely long wire means what? When you have an infinitely long wire means the ends, these are extending from minus infinity to plus infinity. All right, both the ends are extending. So what is infinitely long? Means you cannot obtain its length. It's not a definite length. So how can we calculate Gauss theorem? How can we use Gauss theorem? So for that purpose, what we can do is, see, we can choose a portion only from the entire long wire. Look, the entire big wire calculation from the entire long wire is impossible. For infinite things, you can never calculate anything. So what we can do, we can just take a portion of it. Let's not extend it. Let's just see it's from infinity, minus infinity to plus infinity. So we have just taken a portion of it. And see, wire is completely open. So what we can do, we can just draw a cylinder around it. So that cylindrical surface will act as the Gaussian surface. All right. So electric field is present everywhere. See, these are the electric fields which are present. Now see, radius is R. Now when I am talking about the flux, flux is again E dot S, which is equal to ES cos theta, right? Now see, again what I'll do, I'll break up this into parts. I'll have this as the first part, I'll have this as the second part, and this would be my third part. Why? Because you already know a cylinder, it is made up of one curved surface and two flat circular surfaces. So what we'll do for the curved surface, we'll do it separately. Why? Because see, here when we will be plotting the area vector, look, n cap, this will be making angle 90 degrees. So it will be 0, flux would be 0. Here also when we are talking about n cap, so it will either wherever the direction of electric field is, it will be making angle 90 degree, right class? So if angle is 90 degree, we have no flux due to the first surface or the second surface, that is due to the flat surface. This would be ES cos 90 degree, which is equal to 0. The second surface also it is ES cos 90 degree is equal to 0, right class? Now we just have this third surface. Now look, due to this third surface, we will be calculating the flux. And whatever flux we'll get, this will be our entire flux. So see, here even if we take the area vector n cap, look, on this side even if you take, or on the opposite side also if you take n cap, it is making 0 degree. And you know ES cos 0 degree, cos 0 degree, this is 1. So this becomes E into S. Fine class. Now, what is the surface area of a cylinder? You have the radius as R. Look, R is the radius. Small r is the radius of a cylinder. And you have L as the length of the cylinder, right? So surface area when we are calculating, it is the circle, the area of the circle into the length. This is how we calculate the area of a cylinder, right? And if had it been volume, we would have used pi r square L. So this is the surface area, so it would be 2 pi r L. And electric, so what would be the flux then? Flux would be E into 2 pi r L. One more definition of flux we have, if the charge is Q. Can anyone tell? If charge is Q, what would be the flux? Yes, class?
Q by epsilon.
Q by epsilon naught. Very good one. This is your Gauss theorem. See, this will be this would be Q divided by epsilon. Why? This is from your Gauss theorem. This is your Gauss's law. So see, when you will equate both of these, ultimately both of these are giving you the flux, the first equation, the second equation. So using 1 and 2, you will have E into 2 pi R L is equal to Q divided by epsilon. Now one thing class, this is a wire. A wire is a straight line, and for straight line we have one-dimensional surface charge density. So what is the continuous charge distribution for first dimension, one dimension? The continuous charge distribution for one dimension is the linear charge density. Lambda is equal to Q by L. So what is Q equal to? Lambda into L. Put this also here in this equation. So E into 2 pi R L is equal to what is Q? Lambda into L divided by epsilon. Length would be cancelled. What is the electric field? Lambda divided by 2 pi R epsilon. Look, this is the value of electric field that we'll get for infinite Coulomb pi. So one thing you can figure it out that electric field and radius, if the graph is plotted between them, both are inversely proportional to each other. See, electric field is inversely proportional to mass. So such a graph you will obtain. All right. And see, if we multiply, we can write this as E is equal to 2k lambda by R also, right? Look how, what is k? K is 1 over 4 pi epsilon naught. So 2 R, sorry, not R, lambda. Look, 2, instead of k, I can write 4 pi epsilon naught, then this lambda, then this R. And you see, we are getting this equation back. So sometimes in terms of k also, you can write this as this only, 2k lambda by R. Otherwise, just remember this formula, electric field is lambda divided by 2 pi R epsilon naught. This is important, and these derivations come. These are your applications of Gauss theorem. All right, write this down.
Ma'am, could you please explain this again? I couldn't understand.
See, when we are talking about the flux is E into surface area, right? So electric field is E and surface area is 2 pi RL. And we have Gauss theorem also. Gauss theorem
The
says,
start.
yes,
From the start.
this part, this you have not understood.
Yes, like from the start, can you explain once again?
See, this is the disk of the cylinder. Perpendicular to this is n vector. Now you only tell me n vector and electric field, what is the angle made between them?
90 degree.
90 degree. And what is cos 90 degree?
0.
0. So that's why for the first surface and for the second surface, we are getting the flux as 0. So this is completely 0. Now we are just left with the third surface. Now here the n cap, either way, this is making angle 0 degree. And what is cos 0 degree? देखो यहाँ पर ये है, this is the disk. Here you agree that they both are making with the they both are making an angle of 90 degree. अब ये बताओ मरियम, यहाँ पर ये एन कैप जो है वो इलेक्ट्रिक फील्ड के साथ कितना एंगल बना रहा
Um, so
है?
180?
नो नॉट 180. सी, जिस साइड की इलेक्ट्रिक फील्ड की हम बात करें ना, उसी साइड की हम लोग एन कैप को कंसिडर करेंगे. ऑलराइट. सी, इलेक्ट्रिक फील्ड प्लस साइन है यहाँ पे, so it means this is positive, so electric field will be away from this positive charge. So n cap जो है वो भी away हो जाएगा, because it is always perpendicular to the surface, right? तो इसीलिए the angle that is made between them वो हमारा 0 डिग्री हो जाएगा. फाइन. सो फॉर द
Okay.
कर्व सरफेस एंगल 0 डिग्री हो जाएगा, लेकिन जो हमारा फ्लैट सरफेस है वहां पर तो परपेंडिकुलर जा रहा है, सो दैट्स व्हाई उसकी वजह से फ्लक्स हमारा डायरेक्ट 0 डिग्री. सो अब क्या बचा? अब हमारे पास सिर्फ एक सरफेस एरिया बचता है, वो भी है कर्व सरफेस वाला, क्योंकि कॉस तो 0 डिग्री हो गया. चाहे तुम इस साइड से लो, लेफ्ट साइड से लो, चाहे तुम राइट साइड से लो, दोनों साइड से कंसिडर करोगी तब भी तुम्हारे पास 0 डिग्री आएगा, राइट? So what we have, we just have this third surface left, जो हमारा curved portion. सिलेंडर तो ऐसे ही बनता है ना, एक कर्व्ड सरफेस रहता है और दो फ्लैट सरफेसेस
Yes.
रहती हैं.
हाँ.
सो ये वाला हमारे ES आ गया. नाउ सी, कभी भी हम लोग जब वॉल्यूम निकालते हैं तो हम क्या करते हैं, जब भी हम सरफेस एरिया निकालते हैं, वॉल्यूम निकालते हैं, वॉल्यूम के लिए क्या करते हैं, सरफेस एरिया को थिकनेस से मल्टीप्लाई करते हैं. बट यहाँ पे तो हमें सरफेस एरिया चाहिए. सो फॉर सरफेस एरिया व्हाट विल डू, 2 पाई आर, मतलब कि अब जो हमारा सरकमफ्रेंस है उसको लेंथ से मल्टीप्लाई करेंगे, वो हमारा एरिया देता है. सी, वॉल्यूम ऐसे याद रखो, वॉल्यूम के लिए क्या करना है, वॉल्यूम के लिए जो वॉल्यूम है उसको थिकनेस से तुम मल्टीप्लाई करोगे, मतलब सरफेस एरिया को थिकनेस से मल्टीप्लाई करके जाओ. बट यहाँ पे क्या है, यहाँ पे हमारा सरफेस एरिया, तो सरफेस एरिया कैसे निकलता है, जो भी सरकमफ्रेंस है उसको लेंथ से मल्टीप्लाई कर दीजिए. सो व्हाट इज द लेंथ ओवर हियर, पेरिफेरी क्या होता है, 2 पाई आर. सो मल्टीप्लाइड विद द थिकनेस, व्हाट इज द थिकनेस ऑफ अ सिलेंडर, लेंथ क्या है, एल. सो हमारा, एंड वैसे भी याद ही होगा, सिलेंडर का जो सरफेस एरिया होता है वो 2 पाई आर एल होता है. सो हमारे पास फ्लक्स क्या आ गया, फ्लक्स आ गया हमारे पास 2 पाई आर एल इंटू
यार.
एल. Yes. And Gauss theorem हमारा already present है. Gauss theorem is Q divided by epsilon naught. So ये दोनों equations हमारे पास form हो गई and they are giving us the same flux. Ultimately, both are giving us the same flux of the cylinder. पूरे सिलेंडर पे ही हमें फ्लक्स पता चल रहा है. सो हम क्या करेंगे, दोनों इक्वेशंस को इक्वेट कर देंगे. अब प्रॉब्लम ऐसी आती है कि ये चार्ज के टर्म्स, हमें हमारा आंसर चाहिए कंटिन्यूस चार्ज डिस्ट्रीब्यूशन के टर्म्स, जो हमने लास्ट क्लास में पढ़ा. So continuous charge distribution के accordingly, so linear charge distribution यूज होगा यहाँ पे. Why linear charge distribution? क्योंकि हम स्ट्रेट वायर की बात कर रहे हैं. स्ट्रेट वायर तो वन डायमेंशनल चीज है ना, जब तुम सेकंड डायमेंशन तो आ ही नहीं रहा है, कोई कंसेप्ट ही नहीं है यहाँ पर हमारे किसी और चीज का, लाइक लेग इनटू ब्रेड या कुछ और तो हो नहीं रहा है, सिर्फ एक स्ट्रेट वायर है. सो दैट्स वाई वन डायमेंशन, तो इसीलिए हमने यहाँ पर लीनियर चार्ज डिस्ट्रीब्यूशन कंसिडर किया. फाइन. सो लैम्डा इज इक्वल टू क्यू डिवाइडेड बाय, मतलब चार्ज पर यूनिट लेंथ, एक यूनिट लेंथ में कितना चार्ज है आपके पास. So Q would be equal to lambda into L. वही चीज हमने यहाँ सब्स्टिट्यूट कर दिया. So लेंथ तो कैंसिल हो गया. And अब क्या बचा हमारे पास? Lambda divided by 2 pi r epsilon naught, which you can also write it as 2k lambda pi r. Now it's clear?
Yes, ma'am. Thank you.
Ma'am, I have a doubt. In the If we use the formula 2k lambda by r, can we take k's value as 9 into 10 to the power 9?
Yes, if it is given in the question and if it eases your answer. Because see, you will check which one is better. If you think the radius is mentioned and k with using k, this, why have I told you this? Because this helps in calculation. Otherwise, writing 2, multiplying it with pi, then multiplying it with the value of epsilon naught, that lengthens your answer. So that's why using this is better. But just check the question, whatever the question is saying. Most probably the questions are to derive this and plot the graph. If the numerical part is there, definitely use this. This will ease your calculation only.
Okay, thank you.
Look, class, look at this question. Firstly, whenever you have any question about any vector quantity, what you have to do? First, you have to find out the direction as well as magnitude. Both the things you have to calculate, right? Now, for vector quantities, we require the direction. Then only we will be able to figure it out, now that we have to add it or we have to subtract it, right? So what we do, suppose this is the point one, we have to calculate electric field. That point, oh, Look, due to the first wire is having the positive charge only. So due to the first wire, direction of electric field would be away from the charge. Now, if I move towards the left side, I'll go towards the wire, so that won't be away. So it means direction of electric field is this for first one. Can all of you tell me the direction for this electric field due to second wire at point O? Is it right of or left, class?
Right. Towards E1, ma'am. Towards E1.
Towards it. Correct. Though this is a negatively charged wire, but the direction is opposite for negatively charged. We move towards the charge. So if I move now towards the left, that would be away. So I have to move towards. So E2 is also away. So at least this is clear that we have to add both the charges. Why do we have to add both the charges? Because they are in the same direction. So for the net electric field, we'll be adding E1 plus we'll be adding E2. All right, class. Now see, now you just have to put the value substitution. These are infinitely long wires. Let us write it in terms of this only. So this is the distance given. This is the linear charge distribution given. So we don't require anything else. Lambda divided by 2 pi epsilon naught d plus, again for E2 when we are calculating due to this wire. Dimensions are same, lambda and d. So it would be lambda divided by 2 pi epsilon naught. Correct, class. So see, when you add both of these, that becomes double. This becomes 2 lambda 2 pi epsilon naught d. Right? You're just doubling it. So 2 would be cancelled. Final electric field would be lambda divided by pi epsilon naught. Write it down. Let's see the next derivation.
Oh, hey, let's do this shit.
Yeah, your mic is on. Done plus. Now, C class, next case is that we have a long sheet. Now, infinitely long sheet means again the same thing. The sheet is so huge, it is so huge that the dimensions are exceeding up to infinity. All right, class. Now, again, the same similar thing, you cannot take the entire sheet and get the electric field and surface area and the calculation of the electric flux. So, what we have to do, we'll just choose a portion of it. So these curved endings, these are just showing that you have just torn a portion and you have a very small portion. Now the flux part, the Gaussian surface part, what we'll do, we'll take a cylinder. We'll take a cylinder that will be crossing here also, a circular portion. And like this, we'll have a cylinder which will be passing through. So that will help us get the surface area. Now see again, see it's a cylinder, so similar thing, but see there will be a difference this time. Why? Suppose electric field which we are considering. Electric field is this side due to the wire, or both the sides also you can do. Now look carefully regarding the area vector. Look now. Here would be n cap this time. This is making 0 degree. If you take this side n cap, this will also make 0 degree, right? For this opposite electric. But this time when we take the area vector on the curved surface, this is making 90 degree, right? Because we have just shifted the figure. If you put it vertical, it would be again back to the previous case. So this is horizontal, we are getting these type. All right, so flux would be due to which surfaces? Yes, class, which surfaces? Just just the flat surfaces, not the curved surfaces. So this is due to, let's say this is 1, this is 2, this is 3. So flux will be due to the first surface and due to the second surface. This is straight away 0. Flux due to third surface. This is E S cos 90 degree and we have cos 90 as 0. So this is directly 0. Now see, we are left with flux due to the first and the second surface. Now look, the net flux would be due to the first surface, we will have it as ES, right? Cos 0 is 1. And due to the second surface also, we'll have ES because the electric field will be there also. Yes, so this is 2ES. And what is Gauss theorem? This is Q divided by epsilon naught. This is what? This is our Gauss's theorem. Right. Now what we'll do? Everything is same. The steps are same. But it's just that this is a sheet. It's two-dimensional figure. Right. So the continuous charge distribution, which we have studied in the last class, we'll be considering the surface charge distribution. Charge per unit surface area. So charge would be sigma into S. So you can put this as sigma into S divided by epsilon. Let's equate these two. This is 1, this is 2. So this, when you equate 1 and 2, 2Es is equal to sigma S divided by epsilon naught. S would be cancelled, electric field would be sigma divided by 2 epsilon naught. So also very helpful, very important formula. But see, there is no radius term. So electric field versus radius. This simply shows that electric field is independent of R to the power 0. Electric field is independent in the sheet. On this case, I'll explain you. This will help solve all the numericals. But this I'll only explain once you have written it. Write this down quickly. I'll explain you that note pointer will help you solve all the questions from this page. All the questions. I'll just discuss that. First, write this part down first. And plus, one thing I'll tell you, lots of questions are asked from the applications of Gauss theorem, especially the derivations from Gauss theorem. If you have to study something very important from this lesson, start from Gauss theorem, electric flux, Gauss theorem, and these applications. Because these are very important portions and have a lot of weightage. see class how to solve the numericals on this. I'll just tell you this portion because if the question comes, just listen how the question comes first. See, two sheets will be given to you. They'll ask you to calculate individual electric fields at 3 points. I mean at 2 points, either sides of the sheets, like here or here. Or they can give you two combination of sheets and can ask you electric field at any 3 points, here, here, and here. Except for this fact, no other question is possible, right? So individual is very easy. That you can just write sigma divided by 2 epsilon. And that you will be able to manage wherever it is asking. But if double sheets are given, that I'll discuss with you. So that if values are given, that you can put and get your answers. See, suppose this is the point, this point, red dot. And I have to calculate the electric field due to these two sheets. So see, this is the first sheet, sigma 1. This is the second sheet, sigma 2. When I have this E1, this is because of the positive sheet, so it will be moving away. That's why left hand side is the direction. And when I'm talking about the negative charge, I'm moving towards this. That's why this is towards. So these are in opposite direction at this point if the question comes. Right? Now look at this third one. Similarly here also. For E2, we'll move towards the sheet, so it will be in this direction. For E1, we'll move away, so it will be in this direction. Right, class? Now let us just substitute. For the net electric field, E1 would be again sigma 1 divided by 2 epsilon naught. But we'll just, since I'm not putting the values, I'm writing this as minus I cap, so that whenever you are calculating, you can subtract it directly. I'm not just writing subtraction here, I'll write it add because I'm writing it in terms of vector right now. So that I'm writing in terms of direction. Now, whenever you have the question, you know you have to subtract because they are in opposite direction. That's very clear. And this would be sigma 2 divided by 2 epsilon naught into I cap because this is 2 months. Similarly, here also when you are calculating, you are vectorically adding these two. So sigma 1 divided by 2 epsilon naught will be the same, but here this time this would be E1 would be I cap, and rather this would be 2 epsilon naught, this would be minus I cap. But again, you know, both are in the opposite direction, you will have to subtract. Right? Now there can be one more case where the electric field we have to calculate in the center of both the sheets. Fine. Sigma 1 is also present and sigma 2 is also present. So in between we have to calculate. Here is the only case where they will be getting added. Why, class? Because of positive sheet, it will be moving away. Because of negative sheet, it will be moving towards it. So both of them ultimately would lead to the same direction. So when you are adding it, this would be sigma 1 by 2 epsilon naught. See, due to this first sheet, right? What is the direction? I cap. No negative sign here. Why? Sigma 2 by 2 epsilon naught. Because this is also I cap. So you will just add it. Ultimately, what are we doing? We are adding E1 vector plus E2 vector. Tell me, class, this is clear to all of you? Yes or no? At least gives a thumbs up or write yes or no or say yes.
Yes, ma'am.
Others also? Other students? Amna, it's clear to you?
Yes, ma'am.
Soha, Yahya?
Yes, ma'am.
Just write down this question. One last derivation for the sphere part which I was telling. Write this. I discuss. See class, this is electric field due to hollow conducting. Now hollow means no mass is present inside, right? Everything now in hollow conducting spheres, what happens? We call them as non-conducting also. A solid conducting sphere is different, but hollow conducting and non-conducting are the same. Why? Because charges have the tendency to just accumulate on the surface of a conductor. This is a property known as electrostatic shielding, which we'll study in this next chapter. All right, that we'll study in the next chapter. So see, this is the sphere that we have and electric charges are residing on it. Now the same derivation is followed for solid conducting. All right, solid conducting means it's solid from inside also, mass is present inside also, and it is conducting. For conducting means the charges can go inside. So hollow conducting, non-conducting, or solid conducting. This property of the sphere, these properties of the spheres, you will study better in the next chapter. Now see, we'll take three cases. If we choose a point outside, so our sphere would be a bigger sphere, right? So flux, which is ES, it would be E into 4 pi r square. Now what is this R? R is the radius of the Gaussian surface. Alright, R is the radius of this Gaussian surface. Fine, E into 4 pi r square. So 4 pi r square, why? Why not this capital R? Because capital R is the radius of the sphere. Small r is the Gaussian surface, and now we'll be talking everything with respect to the Gaussian surface. So that's why we have E into 4 pi r square. Fine class. Now, again, flux is equal to Q divided by epsilon naught. This is our Gauss theorem. And see, one more thing. This is a sphere and everything is residing on it. It is not going inside. So that's why we won't consider volumic charge distribution. Since it is on the surface, so we will consider surface charge distribution only. Q divided by A. What is Q? And what is the surface area? 4 pi r square, right? So what is the charge? Charge is sigma into 4 pi r square. See, class steps are the same everywhere. Let us equate it. E into 4 pi r square is equal to, what is the charge? Charge is sigma into 4 into 5 into r square divided by epsilon. 4 pi getting cancelled, 4 pi getting cancelled. What is the value we are getting? Sigma into r square divided by epsilon naught into small r square. Fine. So if you see, electric field is inversely proportional to r square. Now second case is exactly on the surface. Now look, the calculations are easier in the second case. Why? Because the Gaussian surface is radius and the radius of the sphere both are equal in the second part. Look, the Gaussian surface is also here because we are considering a point on the surface, and the radius of the sphere is also here. So here this eases our answer. Why? See, E into 4 pi r square is equal to sigma into 4 pi r square. Here was the difference. No? Here we were considering r square, but here we were having small r square. That's why we were getting this type of answer here. Because this r and this r, they couldn't be cancelled. Look here, class. Why did we consider capital R here? Because surface charge density is on the sphere only. Surface charge density means charge per unit area of the sphere. That's why we have considered capital R here. But this small r here, this is due to the Gauss theorem, flux, electric flux. And electric flux is calculated of the Gaussian surface. Alright, that's why we have this. But here both are coincidentally same, right? 4 pi r square, 4 pi r square. So electric field is just 3. This was sigma, this was epsilon naught also here. Right, so electric field is sigma divided by epsilon naught only. And see, for conductor, I have told you that all the charges are residing outside. So if all the charges are present outside, they are residing outside only. There is no electric field inside. So directly for your third case, inside it is field. Now see if you plot the graph. This is how the graph would look like. This is only there in your syllabus. The inner one, no, where the charges are present inside, that is for your JEE and NEET syllabus. That is not for CBSE. You just have this one case in your syllabus. That's why we are discussing this. Now look, class, if you plot it, be careful and listen carefully. This is 0, means the center. This is R is equal to capital R, means the surface. So any point from the center to the surface is inside only, right? Any point from the surface to the surface to the center of the sphere, that's considered as inside only. And any point outside the capital, any point outside this capital R, this is considered as outside. So look, from the center it's 0, to the surface it's 0, right? From the center to the surface this is 0. So this is 0, no electric field. E is directly proportional to R to the power 0, means no connection with the electron. Inside it is 0. Then at the surface, we have this value sigma by epsilon naught maximum. And then it is inversely proportional to outside. Tell me, class, this is clear to all of you?
Yes, ma'am.
All right, write down this derivation as well. This is the last topic for this chapter. Now we'll start with potential straight away. Yes, class. So this completes with the chapter. Now in the next class, we'll start with electric potential and capacitance. So you all can leave. Any doubts if you have, you can ask. Otherwise, we'll start the next chapter in the next class. Thank you, class. Goodbye.
Thank you, ma'am.